I wrote here, lesson 1, work. In physics, work has a specific meaning. It is not doing something that makes you tired. Instead, work is done on an object. When you do work on an object, you're giving that object energy. You're transferring energy. If we're doing work on an object, here's our physics definition, 2 things must occur. Number 1, a force must be acting on the object. F equals ma, which means the object is going to accelerate. And secondly, the object must move through a distance in the same direction as the force. Work is a scalar. The symbol for work is capital W. Now, the symbol for west is also capital W, and the symbol for watts, which is a unit, is also capital W. So a W by itself on the left side of the equal sign is going to be work. I've gone on my rant about how we're running out of letters in the English language. So work, I'm going to write out the English, is force times distance. Am I hearing a small faint phone going, playing music or headphones or something like that, Nick? Okay. Oh, was it back there? Okay, outside. Gotcha. We're going to write it then that this is the equation that you have. Although I almost always put a times sign between them, because FD is also an abbreviation for something else that you don't know about, but I do, and it just irks me. So I almost always write force times distance. What are the units? Well, we can figure it out. What are the units for force? Newtons. What are the units for distance? So work is measured in Newton meters, but this unit is so important it has a special name. We measure it. Work is measured in joules. Symbol, capital J. This equation, force times distance, only works if you are dealing with a constant force. Some of you that are signing up for me with Physics 12 next year, when we start looking at rocketry, as you go further from the Earth, what happens to the force of gravity? Does it stay the same? Gets weaker? We have to bring out a much more complicated, literally about 9 lines, taking up a full page to do the work to find work. The joke I make is the work you'll be doing to find the work to put something in orbit is the most work you'll be doing of writing. And that's because the force changes. As long as we're staying near the Earth, which we will be this year, gravity doesn't change much in the first few kilometers, so we'll say it's constant force for work. And if we're pushing something, constant force. So, example 1. How much work does it take to lift? Underline the word lift. This is a bit of a trigger word. A 12-kilogram mass from the ground to the height of 9.5 meters. Oliver, what's this question asking me to find? How much what? Work. Yep. And our new equation then is work equals force times distance. When you lift something, what force are you doing work against? It's meant to be really obvious. Looking for a word that begins with the letter G. Gravity. Okay? Now, when you lift something up, the force that you apply up, assuming you're doing a constant force, will be exactly the same as gravity down. I just finished saying that the distance and the force have to be in the same direction. I am going to say that we can go mg, and because it's a vertical distance, we often use the letter h for height. Now, I got to be careful, because you're going to say to me, Brian, wait a minute, gravity's down and h height is up, and you said they had to be in the same direction. What I'm saying is, I know if I'm lifting something and if I draw the free body diagram, the force that I am lifting up with is going to be the same size as gravity. Get the obvious one, and we are accelerating up. Okay? Is that all right? We're going to redefine this special equation a bit differently, and you'll see it's on your formula sheet a bit differently as well. But Oliver, what's the mass? What's G? Ooh, we know this one. Don't need to look it up. What's little g? 9.8. We're going to use the positive because work is a scalar. Don't need to worry about direction here. And Oliver, what's h, the height in this question? 12 kilograms. You've seen that lead weight that I have. I packed it away because I'm doing a Pro D on Monday and I'm bringing it to the session on Monday. But you've all seen that big lead fishing weight. That's right around 12 kilograms-ish. 9.5 meters. That's about the flight of stairs in the back corner of my, over there in that hallway. So how much work would it take to carry that up the stairs? What do you get? This is just to give you also an idea of what a really big or really small answer is. All of you could quite easily carry that weight up the stairs. Now, if I asked you to do it like 50 or 60 times in a row, Oliver, you'd give me a stink-eye look. But certainly if I asked you as a favor, could you carry that with me? All of you would say, yeah, no problem. It'd be a bit of oomph, but you could carry it up the stairs. So this is a small amount of work. What do you get? Anybody? Rihanna, what'd you get? 1,000?
1,117.2.
Is that correct, folks? I'll go to, oh heck, 3 sig figs. I'll call it 1,120 joules-ish. Work is measured in joules. Huh? Do I have a student named Cole? Oh, we have to try this. Stand up, Cole. You should be a little flattered, Cole. I did at least say, amazingly, the wall does not move. I suggested you might be strong, right? Pipe cleaners, not pipes, right? Okay, here we go. So, work equals 0 joules. Why? D equals 0. And if honestly, if I had made you do that for 5 straight minutes, pushing as hard as you can, would you get tired? Yes. Are you doing work? No. Work is not tiredness. Oh, Cole was late. We have to have a bit of fun. Pause again. Pushing a box along the floor requires a steady force, a constant force of 22.5. If you push it for 13.6 newtons, how much work have you done? So we're starting fairly plug and chug. We could defic and list everything, but I think we'll say work equals force times distance. Tristan, how big is the force in this question? Yep. You're starting to see why I told you it was worth memorizing units, because you just glance, oh, newtons, force, right? How big is the distance, Tristan? Can several of you type this in a little quicker than it took on the last question so that we can get through this lesson and not have homework for a long weekend? What'd you get? 406? 306? 306 joules. Even? Oh, that's a fluke. Okay. Now, I glossed over something very, very basic. Glossed over, I said work is a scalar. Let's go back here and let's circle that word right there. Because it's a scalar, work lets us handle questions that to try and analyze them with momentum or by letting up be positive or forward be positive and down be negative or backwards be negative. Questions where that would be very difficult, work can handle easily, like hills. Dylan is pedaling his bike up a 19-meter high hill. The hill is 91.4 meters long. The combined mass of the bike and rider is 65 kilograms. And let's say the bike requires a steady force to continue up the hill. How much work would it take if Dylan used a rope to climb vertically up the back side of the hill? So suppose he climbed right here. We would say work equals force times distance. When you climb, how big a force are you having to exert in order to cancel out the force that's acting on you, Dylan? mg. And since that's a vertical distance, let's call it h. Hey, you mean lifting something and climbing, it's going to be the same physics? It is. So the mass of the bike and rider is 65 times 9.8 times 19.
pardon the interruption again. And finally, grade 11.
12103 joules. Now that would be how much work to climb the hill. How much work will you do riding your bike up the hill? Same answer. Same answer. Because work is a scalar. As a matter of fact, Dylan, if you had the hill looking like this and still ended up 19 meters above, it'd be the same answer. It'd be the same answer. Work doesn't care as a scalar. It doesn't care about the path that you used to get to the final location. It only asks, where'd you start? Where'd you end up? What's the difference? And when you're climbing a hill, the force you're doing work against is gravity. Now, this is the amount of work to climb straight up. Could you do me a favor, Dylan? Could you calculate mg on your calculator? Could you go 65 times 9.8? 637? So I'm just going to make a little note here. I'm going to put a little bracket there. This is 637 newtons. What if your arms aren't able to exert that 637 newtons? If I want to do the same amount of work, I need to spread it out over a longer distance. That will lower the force. And that's what a hill does. All a hill does is it says you're going to do the same amount of work to get to the height no matter what, but if you want less force, you've got to increase the distance. We call this a simple machine. A simple machine, a first-order machine, says, look, you're stuck with having to do the same amount of work. You want to lower the force, increase the distance. It's what a car jack does. A car jack, I want to raise the car this far. With the jack, I can use less force, but I have to go up and down. I have to do way more distance to get the same amount of work on the other end of the car jack. So, using my answer from A, calculate the force that Dylan needs to exert to pedal up the hill. Dylan, in the work equation, get the F by itself. Here's another definition of force. Not the most common one, but it's what I would use here. The work that you did is 1203. Going up, was it 1203 exactly, or was there some decimals? Was it 12103 exactly? Yeah. How long is the hill? How much force will you need to exert? As opposed to 637? And I've just explained, Rihanna, why stairs work. We could make them really steep. Heck, we could make them vertical like ladders. All of you would have to exert a force equal to mg. Now that would be the minimum distance. Or, Oliver, we put them at an angle, we'll increase the distance but dramatically lower the force to get the same work. This is one of the nice characteristics about work. It's a scalar. How much work would it take for Dylan to ride to the top of this hill? Well, he's going up a hill, so what's the force that he's resisting? Gravity. What's his final height? Still 19? It was 19 meters before, right? Trying to analyze a yucky path like this with a vector method, you'd have to have a constantly changing angle because the direction is changing all the time. I could probably, Oliver, maybe do it with calculus, but I would dread the task. I'd use a scalar approach. And that's one of, towards the end of the year when you have all these tools at your disposal, or next year in Physics 12, if you ask me, when do I use work? If there's a change in height, change in speed, and a yucky curvy path, then I'm using work. Scalar. What takes more work, lifting a 25 kilogram mass to a height of 4 meters, or lifting a 50 kilogram sack to a height of 2 meters? Why? Force times distance also equals force times distance. In other words, you'll do the same work lifting something heavy a short distance as you will lifting something lighter a longer distance. This is the trade-off all the time between machinery. Any simple machine says, look, you're stuck doing the same amount of work. I can lower your force, but it's going to be at the cost of increasing the distance. You may have even noticed this. You know what? You probably have all grown up with bikes that had gears. My first bike was a standard little kid's pedal bike, and it did not have gears. And so I learned to go up a hill. I zigzagged up the hill. I didn't realize what I was doing intuitively was I was increasing my distance so that I didn't have to do as big a force, because when I was 6 years old, I couldn't put enough force through the pedals to make it straight up that hill. But I could zigzag my way up. Some of you are going, oh yeah, I did that when I was a kid too. Some of you are going, oh, my parents had more money. My first bike was electric with gear. Shut up. So Rihanna, work equals what times what? What's our new equation? And as always, that's 3 equations in one. Force equals work over distance, and I guess distance equals work over force if I ever happen to have only that. Except there was a restriction. We said that the force had to be, I'm looking for word begins letter C. What if the force is not constant, but changing instead? Here's your second definition of work. You're going to get from me 3 definitions of work. And so when a question says, how much work? You're going to run through a checklist. You're first of all going to say, did they give me a force and a distance, and is the force constant? I'm going to use work equals force times distance. Is it not constant? Here's our second definition. It's also the area under a force versus displacement graph. So here is a graph. What's on the y-axis? Force in newtons. What's on the x-axis? There's a force versus distance graph. And do you notice the force is not constant, it's getting bigger. It starts out constant, flat for a bit, but it's getting bigger. Mateo C., what is this asking me to find? Keep going. Keep reading. From where to where? So all of us right now at 2 meters go d d d d d d d, and at 5 meters go d d d d d d d d d d d d d. Sound effects optional. The answer is going to be that area. Now there is a candy available. I always ask. This first question is not the candy question. What shape is that? What do you call a shape that has 2 parallel sides and 2 sides that aren't parallel? Begins with the letter T. It's a trapezoid. Okay, that's not the candy question. The question is, does anybody here know the equation for the area of a trapezoid? There is one. And every once in a while I have a nerdy kid who's looked it up out of curiosity and knows it. Do you know it? Pardon me? You can remember it or you don't? You can write on the board? I have to find out because there's a candy here. Normally I'd say either don't write this down or write this down. This is purely optional if you're a nerd. If you have a trapezoid, if you call one parallel side little a and the other parallel side little b, and then you call the side linking them at right angles h, it's a plus b times h over 2. But there's a reason why I've never bothered memorize. Okay, that's a lot. I've memorized. There's a reason why we don't teach it. Any trapezoid on the planet, and now you are going to pick up your pencils, can be broken into this. A rectangle and a triangle. And those you have done area equations for. So that trapezoid equation, area equation, while lovely, it's redundant. And you've had me enough to know that if something is redundant, it's low on my list of things to try and memorize. If I got something that works fine and it's only one extra step, I'm good with it. So let's call this bottom area Roman numeral 1. Let's call this top area Roman numeral 2. We're going to find the area of each of these and add them together. By the way, I like example 7. I like example 7. I like example 7. Nice question. So what's the area of shape 1? Well, shape 1 is a rectangle. How do you find the area? What's the equation for the area of a rectangle? Length times width. Looking at this rectangle, what's its length? Please count carefully. I think 3. What's its width? Look at the scale carefully. It's 1 square, but it looks like we're going up by 2s. So do you agree with me? It's 3 by 2. Sierra, in your head? Yep. Area number 2 is a triangle. What's the area of a triangle? Give you a hint. It's something times something divided by something. Okay. It's base times height divided by 2. It's almost length times width divided by 2. Because a triangle, people, is half a rectangle. Oh, divide by 2. So, looking at this triangle, how long is the base? Also 3. What's the height? Not 8. 6, isn't it? Right? I know it's 8 high there, but it starts out to... By the way, I'm glad you did that, because that's a foolish mistake kids do on the test, and it drives me crazy. Divided by 2. Christian, in your head? No, in your head?
I can't do this in my head.
Sure you can. What's 6 divided by 2?
9.
Yes, not 9. Yes.
The number.
Ah!
Equal.
I had you all set up for the punchline there. And then, Christian, maybe you can even add them together in your head, because that would be the total area. 6 plus 9 is? By the way, go 9 plus 6.
15.
Right? I never add 9. I always say, it's going to be 9 plus 6 is 10 plus 5. Right? And I'm going to say you can probably do 10 plus. Pretty easy. So you have 15. Units, it's work. What were the units for work? I'm being serious. I'm trying to, you guys know I try and do a lot of math in my head, and I'm letting you know some of the tricks that I had to learn as a kid because I didn't grow up with a calculator. I'm that old. I graduated in 1987.
Nice. High five.
Well, some people might be thinking 18, right? Okay. So now, Emily, we have 2 definitions for work. Joel, the first one was the equation. What was the equation for work? That's in the box. But that's, go look.
Wait, what?
Equation for work. It's on the first couple of lines of the handout. Force times distance. Please note, it is on your green formula sheet, yes? And just make sure you know where it is. This is one, although you don't have to memorize. Probably, Oliver, during this unit, you will memorize it because you get sick of looking it up. The same way you probably memorized P equals MV last unit because you got sick of looking it up. However, what was the restriction? This requires a constant force. There's a second definition for work. It's the area under a force versus distance graph. How do I know when to use that one? It's going to be stupidly Captain Obvious. They gave me a force versus distance graph. No graph? You're not using that one. There is a third definition of work which we can't get to for a few days because I got to teach you some more. How much work was done in moving this unknown object 10 meters? I guess it's going to be oh, it's going to be that area, which again is a trapezoid. And if you want to use a plus b close bracket times h over 2 area of a trapezoid, you can. Me, I tend to just say, all right, this is going to be a rectangle and a triangle. I usually do the rectangle first because it's easier, and you've had me enough to know that I always like to do an easy step to get my brain flowing, and then I'll do the nasty stuff. Christian might even try this in his head because it's his 10 times table. So Christian, are you ready? I'm coming back at you. Area of 1, so it's length times width. Looks like the length is 10, and it looks like the width is 20. In your head? Yes! Get a little nerdy adrenaline rush. This is what I feel all the time when I do math in my head. You'll make a little math nerd heart go pitter-pat. Shape number 2. And by the way, really those are the only 2 you need to know, triangle and rectangle, because any trapezoid can be broken into a triangle and a rectangle. It's going to be base times height divided by 2. The base is also 10. The height of this one, also 10, yes? Divided by 2, what's 10 times 10? Divided by 2? In your head, what's 200 plus 50? Yep, that's how much work was done. Now, right now, Christian is both happy that he was able to do the math in my head, but I can see from his body language, part of him is saying, so big deal. So what? Actually, huge deal. I haven't yet told you what else work is. It lets you figure out how fast something is traveling or how high in the sky it will reach if you throw it. It lets us analyze roller coasters. Oh, yeah. We'll get there. Let's kick it up a notch, and this is also going to be good review. I think last unit, there was a couple of times in the momentum homework when I said, here's an optional nasty question. One of them had a mu in it. The fact that I see that, you know what I'm already thinking this might be a job for? I'm already thinking, Tristan, I might pull another free body diagram. Let's find everything out. Here we go. A box is being pushed along a floor, but now instead of ice, there is some friction. The person pushing applies a force of 525 newtons over a distance of 22 meters. Nick, what does A want me to find? How do I find work? Did they give me a force?
Yeah.
Did they give me a distance?
Yeah.
And this is really, I'm going to be fussy. The work done by what in part A? So it's going to be the force from the person, which is 525 times 22. This might be moving one of those gym benches across the gym by sliding it. This is how much energy, how much work that would take. What'd you get? 11,550? Units? Yep. Jacqueline, what's B wants me to find? Did you say work? Work equals force times distance. I know it's not the area underneath a force versus distance graph because they didn't give me a graph. Keep reading. How much work is... I cut you off on purpose. I think that's going to be the force of friction times distance. Friction is what times what? I recall that phrase. Something is twigging. You know what? I think this is a job for a free body diagram. Over here, I think you have room. Let's put the box right there. Let's represent it with a dot. What are the forces acting on it, Jacqueline? Get the obvious one. I totally agree. What else? Normal force, right? Is it sinking to the ground like quicksand? Is it flying like Superman? What else? Well, there seems to be an applied force, and that looks like it's 525 newtons. And then I guess friction is that way. I'm kind of guessing the applied force is winning, I think. If not, I'll find out because I'll get weird numbers and weird answers. So, okay. Back to my question. Friction is what times what? Mu times the normal force times distance. Hey, this is good review. Jacqueline, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which one? So you're telling me the work done in overcoming friction is going to be mu mg, and then the d drops down? Hey, Jacqueline, what's mu? I don't know. What's mu with you? Come on, you've missed some of these jokes. 0.25, yes? 124. G, 9.8. Distance, 22. What do you get? So now we're leaning on Nick for a change. Say that again. 6? Is that right, folks? No, it's not. Well, it is, but ready? I've kind of fooled you here. I said work was force times distance, but I said the force and the distance had to be in the same what? Do you remember? If not, go look at the first page. What did I say? They had to be in the same direction. The distance is that way. Friction is... How could I show that friction is in exactly the opposite direction? What? Sure. This is not saying backwards. What this is real, because it is a scalar. Work is a scalar. What this is really saying is you lost that many joules of work to friction. So from the original 11,550, that many were lost to friction. What would be a good way to indicate a loss? Negative. Less than. Minus. So then, what's the net work done on the box? It's going to be sort of winner minus loser, except what I'm really saying is you're starting out, you're doing 11,550, but you're losing 6683.6. The rest of it is what's going into causing this box to speed up. The first 6,683.6 joules of work are only just keeping it going, overcoming friction. What do you got? Dylan's yawning. Really? Really? Ooh. It's true. This is by the way, this is the foundation lesson. I got lots of cool toys and videos and demos coming up. Trust me. What'd you get? Rihanna, what'd you get? 4866.4 joules. So 4,900 joules. We went to 2 sig figs. So work is force times distance. Work is also the area under a force versus distance graph. Since the force times distance equation has 3 variables, as far as I'm concerned, it's 3 equations in one. And then we can talk about, okay, if it's in the opposite direction, we can call that energy loss, work lost, negative work. Not a direction, not really saying backwards. I'm saying, well, you had a force canceling out your force. By the way, the other way I could have done this is I could have gone winner minus loser. Who's winning? I could have found the net force, and really work is net force times distance, and I would have got exactly the same answer here. What's your homework? I think almost everything. So let me see which ones I'm going to cross out. I think I'm good with all of these. And you got lots of time. 22 minutes. So you might even not have homework for